So we're talking about pipes, and so I don't know, these are just a few things. So we've certainly talked about dams. Certainly dams are fed by a penstock, a tube from the upper reservoir down through a powerhouse and turbines and out into the rivers. And I guess when that goes wrong, if you have 100 meters of head or 200 meters of head, then all of a sudden things go wrong in a big hurry. And so I'm not sure where this is or really even when it was. I don't see a date on it. But this is the powerhouse, I think, which is at the bottom end of the penstock, the tube that brings the water down from the dam. Typically, there would be a tunnel probably big enough to walk in, feet, 5 feet, 10 feet across, 3 meters. Close to the powerhouse, they're usually lined with steel because the pressures are high enough just due to the static head. If you shut off the flow, the static head would be equal to 100 meters of head, so the pressure you can work out as being P over gamma W, so head times unit weight, is large enough to be able to just blow out the rock that's around. And so this, I think, is some closed caption footage of what was going on. Oh, I don't know what that is. Oh, this is something else. This is the Veillon disaster in Italy in the 1950s. A big landslide occurred into an existing dam that actually pushed all the water out of the dam over the top and down the valley and wiped out the downstream villages. And so we looked at Malpassé, I think, when we talked about pressures on structures, pressures on dams. This is slightly different in that it was a landslide into the lake, pushed the lake over the water of the lake over the dam, and then it rushed downstream in a relatively constrained valley in the Italian Alps and killed, well, you're going to see, I guess. So not related to pipe flow, really, except there'll be pipe flow within the dam. Typically, these dams are built because they're high elevation. They trap the water. You have a reservoir that's stored there, and then you have a powerhouse which is down at the river base below. So you get the maximum elevation drop because we know that power is equal to volumetric flow rate times density. Head is equal to power divided by mass flow rate times G. So if you switch that around, then you get the power is equal to the height, the head height, the mass flow rate times gravity. That's it. And so you want to get the largest elevation difference between the reservoir and where it discharges through the turbines, and you want to get the maximum velocity you can get, which is also as a function of that height as well, just the distance that it's falling. And so it looks like a reconstruction. I wonder if the Smithsonian Channel will get in my case for showing it on a YouTube video. I don't know. But anyway, that's a follow-on, I guess, from the Russian television unfortunate situation. I don't know why I have this. Perhaps nastier things, but necessary things. Sewage pumps. Pump sewage along pipes. Bladders, they typically work just like a storage tank within a house. We have a well. The well brings water into the house. It's stored in a storage tank, but it's kept under pressure by a bladder which has air behind it. Air is much more compressible than the water that it's pushing out. And so when you open a faucet and drain some of the fluid, then the air is very compressible. It expands. It changes the volume inside the tank, but not with very much pressure change. It keeps its pressure as it does. So I'm not sure why I ever had a bladder pump on there for sewage, but anyway. What else? We've seen the buoys, and so I won't bore you with that again, but again, pumps. Deepwater Horizon, certainly within your lifetime, 2010 was it? Yeah, 2010, April 2010. So a drill rig finishing off a well in the Gulf of Mexico, drill pipe goes down, they tremmy cement around the outside of it to be able to seal it, to be able to lock it in, and it wasn't locked in very well. And gas from the hydrocarbon reservoir came up the outside of the pipe and ultimately onto the drill deck and caught fire, big explosion, killed a bunch of people, and cost BP, who are the owner of the drill rig, something like $40 billion or something, some ridiculous amount of money. And of course they had to put money into a fund to renovate the Gulf, which is still administered. Okay. And so maybe topical with COP26 going on now. I guess the interesting stuff for the politicians is done now after 2 days. Now it's 2 weeks of people, I don't know what they do for the rest of the time, to reach some kinds of agreements, voluntary agreements about reducing emissions. But of course, a big part of that issue is the penetration of renewables, the relative costs of renewables versus fossil fuels. We're traveling up in Scotland actually 2 years ago, and actually it's amazing. These offshore wind farms in the former North Sea, so this used to be an oil reservoir, the North Sea oil, this is the North Sea, all offshore, has spawned on these shallow shelves offshore wind farms where the winds are quite steady and quite fast, and so are quite predictable in terms of power. And so wind and solar suffer from the problems of dispatchability, as it's called. So you only get power when the wind blows or the sun shines, so clearly you don't get solar power at night, so you have to use batteries. And using large-scale batteries is not very easy. I guess you can get Elon Musk to put in battery farms because they're used to that technology for Teslas, and that's a growing market. But one big way to do that has been pumped storage. It's been around, certainly Denoric was a scheme that was built in Wales where we took some students in 2003 to one. Drakensberg in South Africa is another one. The principle is pretty straightforward. You use the water potential as a battery. So at night time when you're running your nuclear power plants, it used to be that you can't switch off. You use the cheap electricity to drive water into the upper reservoir, and then when everyone puts their toasters on at 7 o'clock in the morning, you let it shunt down through it to be able to generate power. And so we've talked a little bit about that. I'm not sure the point that this movie is making exactly. Certainly, since we said before that the amount of energy you get from something is the mass times the elevation, that's the potential energy. And so to get the maximum amount of power out of it, you need a high flow rate and a large head. They both feed into each other. I guess you can make the mass flow rate larger by using a big tube between the upper reservoir and the lower reservoir. And so to maximize that, if you maximize the height to which you raise it, you maximize its potential. And so you need to look for a country where you have both elevation and plentiful water. And so Norway works, Sweden would work less well, the Netherlands would work terribly because they're flat as a pancake. There's basically the delta or the estuary for the Rhine River. And so the idea is that you could store your power shunt your power to Norway, have it stored in the way that it's used in pumped storage, and then bring it back on demand and have a smart grid that really distributes this around quite readily. The other thing which I thought was interesting, I was using a paper just yesterday of an idea that of compressed air energy storage, CAES. The idea is that when you have the windmills blowing or the wind turbines blowing, you have electricity. You use that electricity to compress air, and you put that air underground into depleted oil reservoirs. This is the North Sea oil reservoir. And then you use that seasonally, so that when the wind blows hard in the winter, you store some of that energy, and then you use it in the season when it's not blowing so hard by just recovering it. So not so much on a daily basis. So this is kind of on a daily basis, up at night, down in the daytime. This would be pump up the reservoir when in the season when the winds are strong, and use the energy in the season when the winds are not strong. So it's not a diurnal cycle, but a 6-month cycle. And actually, I don't know. This might be it. I don't know if there's I don't know where Almafojoa is. There's actually a pump storage scheme in northern Pennsylvania. It's up in it feeds into the Allegheny River, so it's in the northern part of Pennsylvania. I guess I could actually look for it. So pump storage. Do you know, guys, where it is? Must be up where you are. Seneca Pump Storage, is that it? Muddy Run Pump Storage? I don't know. I want images, I guess, right? We don't want to look at words.
It's up at the Kinzu Dam on the Allegheny.
Yeah, okay, it's Kinzua, yeah? Where the bridge blew down?
Yeah.
Yeah, so that's it. So here it is. It's, not so much elevation gain. I can't, will it get bigger? Not bad. So artificially made lake in this particular case. Dinorah in Wales, I don't know about Drakensberg and Set, they're all over the place, but those were naturally existing mountain lakes with which would then discharge into a lower reservoir as well. But this looks like it's been constructed and it looks like it's lined. There'd be a powerhouse in here somewhere. The pipes could run on the surface. Usually they're put in tunnels in the ground because they have to resist a fair amount of fluid pressure, the total elevation of this when you shut them down, and you don't want to blow the rock out. And if you're using, I guess if you're using the dam here with the turbines, if you're using this dam to generate power as it goes from the upper level here to the lower level of the river, I guess you could probably pump up here for pump storage and then discharge here and then discharge it down using the same turbines in some way, right? To be able to use one set of turbines instead of a whole bunch of them. So that's that. So on, we have a nice chat this morning. We don't have much to deal with in terms of our what we'll talk about today. So we have a bit of time. And so the other thing where pipes are present, penstocks and dams are part of that equation. Pipes would be petroleum reservoirs and gas reservoirs are replete with pipes at all scales. And so the obvious ones are that we talked about the San Bruno disaster. Apparently, I like disasters for some reason, where in southern San Francisco near the airport, a gas pipeline ruptured and caused a fire. Obviously, that is fed into by drill pipe, which goes into the pipeline. And drill pipe is a normal well, amazing technology that you can drill maybe a few kilometers horizontally to be able to stay within a reservoir and then put casing down it. And then, I don't know what they're going to show here, but then hydraulically frack it to be able to get the hydrocarbons out of it. And of course, these rocks are such low permeability that if you don't do something to break them up and change the drainage path. So this is Deepwater Horizon. This is the cement being pumped down around the outside of the annulus of the case, so the casing is sealed. This looks like shape charges to be able to blow their way through the casing to make little holes that you can then hydraulically fracture by just pumping fluid at very high pressures. And then once you've done that, you pull everything out and you try and produce it. So the idea is that in the reservoir, you could think of the reservoir as being a whole bunch of little capillary tubes. Now, we talked about a capillary tube for fluid rise within a capillary tube in perhaps week 1. So you can also think of capillary tubes as being tubes that make up the porous media. Take the pores within the space and just represent them as a single very thin tube and have a whole bunch of parallel tubes parallel to it. And you can work out what the permeability would be based on that. You can work out the permeability of these fractures based on a parallel-sided duct, which we looked at the solution for briefly in week 8, I think it was. And then you can look at the transmission characteristics of the well itself in terms of the pipes that we've talked about in this section of the class. So I guess just bringing some practicality to some of the things that we're talking about. So pipes, although I think they're kind of mundane, they're necessary, I guess, in terms of what we're dealing with. And I think in a good sense in terms of exams and those kind of questions is that they're somewhat predictable because they're a little bit formulaic at least. So that's kind of where we are. So let's finish off the things that we'll talk about on pipe flow. So Friday we'll talk about pipe networks. So when you have pipes in parallel or pipes in series or branching pipes, but we'll leave that for Friday. And so really what we have to finish with, I think, are the ideas that we have these type 2 and type 3 geometries. And we kind of already dealt with it, right? We had this matrix which was in terms of dimensions. And I'll see if I can remember what the different types are. Dimensions were diameter, they were length, and they were roughness. And the derivatives of those, they were flow rates, and flow rates would be either velocities or volumetric flow rates, either one. And what were the other things? Head losses. And depending on which ones of those we knew, I guess this would also be delta P, and etc. And it was in some ways also pump magnitudes, because we made the argument last time about how if you have flow between an upper and a lower reservoir, just like the pump storage streams we're looking at, if you don't have any resistance in there except for the major losses in the pipe, it will flow at some velocity which is defined by that head geometry and the size of the pipe. If you then put something in the pipe to be able to slow that, a pump or a turbine, then the energy you get from that pump is directly related to the amount of velocity that you've reduced from its natural flow rate, and you're gaining that as work that you're doing in the system. And so we called these type 1s, type 2s, and type 3s, as you see before on the top left. And I guess the easy ones were when we know what this is, and we know what this is, and we want to calculate the head loss. It's easy because the Reynolds number is always defined in terms of the velocity and density and a characteristic dimension, hydraulic diameter as we saw last time, and viscosity. And maybe just at the bottom, I know you don't want me to write the Bernoulli equation, but I will write the calculation sequence that we use, right? It's either force equals a loss coefficient times v squared over 2g, or sorry, not force, friction factor equals, you should be correcting me here, shouldn't you? Length over diameter v squared over 2g. So we have Reynolds number, which is equal to a velocity, a density of the fluid that's flowing, and a hydraulic diameter and viscosity. We defined hydraulic diameter for non-circular segments as 4 times the area over the perimeter, and we'll do an example a little later. And we can then go to calculate, so we calculate velocity, we calculate friction factor, and we circle back to be able to check that we've closed the loop. So if we know what the velocity is, we always know what the Reynolds number is, so we know definitely, absolutely what these friction coefficients are, or these magnitudes are. So this is assumption always that these are typically turbulent in this particular case. So type 2, we calculate the flow rate. So I guess we calculate the flow rate from prescribing a head loss and the piping dimensions. And the third is the most difficult, in that we want to be able to dimension the system as a function of a desired flow rate out of your faucet and a desired head loss that you have between the tank in your attic or the tank in your basement that has a particular pressure in it, and you want to be able to get out of velocity. And so those are the kind of the calculation sequence that we've talked about. And so I think we've probably done that to death. So I just was going to go through a couple of examples. So this one, not this one, and this one. So I guess there's a type 3 one, which is this one, and one type 2 one, which is this one, determine the flow rate. So that's all I was going to do. That's why I was spending some time looking at some movies this morning. So what is this? The pump shown here adds 25 kilowatts to the flow. It has a flow rate coming out of here of volumetric flow rate is equal to 0.04 meters cubed per second, which is this. What is the flow rate that you get if you remove the pump from the system? It's made easy made tractable by assuming a friction factor. So I guess that means probably it suggests that the flow is turbulent, although it doesn't really matter and the reason for that is that the friction factor is only constant if you're in this part of the graph, right? So what was it, 0.4? I don't remember. If it's 0.4, it's up here somewhere. And so the fact that that is constant means that it's turbulent, although I don't think that matters for the question. And you don't know what the height of the head in the tank is. And so you first know that when the pump is on and supplying 25 kilowatts, that the flow rate is equal to this flow rate. And so you could solve to find out what the magnitude of this head is first, because you don't know that. And then once you have that head calculated, then you can take out the pump power and see what the flow rate through the system is. So I guess it's both systems, right? So it's doing a calculation once to see what this is. And so if you write it between upstream you can choose a place where the pressure is 0 and the velocity is 0, which would be this. Downstream would be where the velocity is not 0, but certainly the pressure has to be 0 because it's coming into the atmosphere. And so you can write Bernoulli in those terms: upstream pressure, upstream velocity, elevation, pump head, downstream pressure, downstream velocity, downstream elevation, and also the losses within the system. And so of these, I guess both pressures would be 0. So we're going to solve first for the magnitude of this elevation. This elevation would be Z1, which I guess we don't know, hence the question mark. But we know what Z2 is. I guess if we choose the datum at that point, then this is just Z equals 0, obviously. We know the velocity in the upper reservoir. If it's a big tank, then the velocity is 0. So it's convenient to choose that. We know that the pump head is equal to 25 times 10 to the 3 divided by density of water times gravity times velocity times area, Q, right? Remember that it's the velocity, well actually it's not, we already have Q, right? Probably easier to write this, we have Q. So we know what the pump head is in terms of this. So we know Q, we know density, 1,000 kilograms per cubic meter, we know gravity, and we know the power in the pump. So we know everything in HP. V2 is not 0, it's going to be equal to, V2 is equal to Q divided by A2, right, in terms of this. So we know what V2 is, and we need to know what the frictional loss is. So the frictional losses We know that the friction factor wasn't 0.04, it's 0.016. Length is 30 meters, and diameter is 60 meters. So length is 30, diameter is 60 millimeters, which is 6 centimeters, which is 0.06. I guess. V squared is the velocity in that pipe, and so V is equal to Q over A pipe, whatever it is. So cross-sectional area using the 60 millimeter diameter. So A is equal to pi d squared upon 4. So, yeah. So out of that, if we're not getting too messy, I guess these are the things that are marked. These are the things I've said. V2 is equal to Q divided by A2. V is equal to Q divided by A. So we have both the magnitude of the velocity V2 and the velocity within the pipe, what we've called V. And so the only things we're left with are that Z, we'd be left with Z1. So this is really Z, right? Which we don't know. This we kind of know, but we haven't calculated yet. I guess the calculation is right here. 2.5 times 10 to the 3. I guess I wrote it somewhere. 2.5, 25 times 10 to the 3, not 2.5 times 10 to the 3. G times the volumetric flow rate. And this is G times the unit weight of water, right? So this is the unit weight of water. So we also have HP. So out of this, we have HP. We have, this must be V2 squared over 2G. This must be the friction factor. This is length. This is diameter. This is V squared over 2G. So in other words, it's this term here. And if we add those two together, we end up with the only variable that we don't know is equal to this C, and it turns out to be this. So that's it. So if we know now with the pump going, even though it would probably flow, almost certainly would flow on its own, right? If you just leave it to run. The flow rate that we have in the system is conditioned both by this head and the fact that we have a 25 kilowatt pump that's pumping. So the second part of the question is, if you turn this off, so HP goes to 0, then what is the flow through the system? Now that we know that Z1 is equal to 69.5 meters. And so without a pump, the calculation would be just to write Bernoulli. I guess it would be no different from before. The fact that we had, so we'd write this equation out here. It would be Z1 plus HP. HP is equal to 0, is equal to some velocity squared. This would be the velocity in the fitting. And so we'd have to realize that this velocity 2 squared over 2G plus the friction factor times length over diameter times velocity over 2G squared. These two velocities now are linked to each other because they're both linked by a flow rate Q is equal to velocity 2 times area 2, and that's also equal to velocity times area. So they're intrinsically linked to each other, as in this. And so we could choose to write it in terms of either V2 or V. I guess it'd probably be better to do it in V, because V is, well, actually it doesn't matter. You could use either one. But the point is that by using continuity, basically continuity here, you only have one unknown in terms of a single velocity and a single elevation, and you can solve for that single velocity because we know that if it's turbulent, the friction factor doesn't change from 0.016. And that, I think, is what's done here. This is the height z. It's written in terms of the first term. This is friction factor. This is length over diameter. This is the velocity. And this is the same velocity from these, since they're linked to each other by the ratio of the areas. And you can solve for square rooting this, and you come up with a single value. So it's fine. So I guess that is both a type 1 problem, right? The first one, if we go back to this. The first problem was defining the velocity and calculating the flow rate. The height of the upper tank, 69.5 meters. And the second part was solving a type 2 problem, which was solved for the flow rate in the system if you know the height of the upper tank and you also know all the geometric characteristics of your system. So not so straightforward. You can also, so the other thing that happens in these, and I won't do this, is that if you have sometimes flow rates, you end up solving sometimes a quadratic equation to be able to get the solution. In this case, the quadratic equation only has one term in it. It has a squared term for the v squared, but it's only one term. You don't have a v and a v squared term. But sometimes you have to solve a quadratic, as in this case. So let's not bother doing that. The type 3 problem is to solve for dimensioning a duct. And so the idea here is that you have a duct, I guess in plan view or in isometric view, it would look like this. You want to flow along a duct, which is obviously non-circular. You have a flow velocity which is flowing into it, and you want the flow rate to be equal to 100 meters cubed a second, which is this term here, and you want the pressure drop from upstream to downstream to being delta P, which is delta P over gamma equals HL. And so the pressure drop to be not more than 40 millimeters of water. So I guess this should be 40 millimeters. But 40 millimeters of water. And so 40 millimeters of water means that this should also be the density of water, even though the fluid that's flowing through here is air. So I think you probably have to be a little careful with that. So the pressure drop is equal to 40 millimeters of water. So delta P would, if just by multiplying this through, delta P would be equal to this term here, not 40 meters of air, which would be, or 40 millimeters of air, which would be 1 kilogram per cubic meter times gravity. And so the deal, I guess, here is to figure out what you need to know for Bernoulli. There's no pump in the system, so you can write Bernoulli between upstream and downstream with frictional losses in it. There's no pump in it. The elevation is probably easiest to have horizontal, and so these would both be 0. The pressure drop between upstream and downstream is not going to be 0. But the velocity between upstream and downstream these are going to be the same, and so these cancel out, not because they're 0, but because they just cancel out. And so if you do that, then you're left with an equation that looks something like P1 minus P2 over unit weight of air is equal to, everything else drops out, right? Friction factor, length over diameter, v squared over 2g. And the rub is, of course, that you don't know what the d is. You know what the L is, that's a meter, right? 50 meters. So I guess this is 50 meters. So how to do that? Well, I guess the basic deal is to take this duct and to be able to write all the variables in terms of one parameter. And one parameter would be unfortunately used H in this term, not to be confused with HL. So in the terms of the parameters, we said that the hydraulic radius, which we didn't, the hydraulic diameter is equal to 4 times area over the perimeter, is equal to 4 times the area would be, the area is 3H times H. The perimeter would be 3H plus H times 2, which is 4H, right? So, half the perimeter is this length plus this length. That's 3H plus H times 2 is this. And so we have the, this comes out to being this term here. So the hydraulic diameter is equal to 1.5 times this dimension. The Reynolds number is equal to density of air times velocity of air times the hydraulic diameter divided by viscosity. And so since we know that this hydraulic diameter is equal to 1.5 times H, we can also write somewhere the Reynolds number in terms of that, which I think is this here, 1.5 H. This is velocity, and this, we've never used this term, but kinematic viscosity is equal to the dynamic viscosity divided by the density. So this term here is the kinematic viscosity. So this here is the kinematic viscosity, nu, which is this. And so we can write not only the hydraulic diameter in terms of H, but we can write the Reynolds number in terms of H. So why don't I outline those? We can write Reynolds number in terms of H. Okay, and we have the Bernoulli equation. And so this is Bernoulli equation. Written above. So because we've only got this term, the upstream pressure and the downstream pressure survive, the elevations drop out, the velocities drop out, and the only term is this major head loss term left in the system. So that's P1 minus P2, if you rearrange it, is equal to the friction factor length. The friction factor is defined also in terms of the hydraulic diameter, equivalent hydraulic diameter, half rho V squared, and we've taken rho density of air here, taken out G, and we've made sure that this pressure here is in terms of 40 millimeters of head, right? This is 40 millimeters times the density of water. Rho G is called gamma W, right? You know, gamma W is equal to rho WG. And so the pressure acting on the system, P1 minus P2, is 392 newtons per meter squared, which is this. So coming back to Bernoulli, or the head loss term, the pressure change, friction factor, which we don't know because we don't know what velocity we're traveling at yet. 50 meters of duct, the diameter, equivalent diameter is 1.5 times H, a half times velocity, no, half times density, 1.23 kilograms per cubic meter, times velocity squared, and we've defined velocity as equal to Q over A. We know what Q is, Q is 100 cubic meters a second, so the velocity has to be 100 cubic meters a second divided by the cross-sectional area, and the cross-sectional area is just 3 times h squared, right? So that's that. And so it seems kind of complicated, but I guess the only things to realize in this are that the principal things that we need to know, which would be a velocity. So too many things are outlined in red, but maybe I should go back in. So we've defined a velocity, we've defined a hydraulic radius, we've defined a Reynolds number. So this is why I say type 3 problems are a pain. And we've defined the hydraulic loss term in terms of Bernoulli. So these are the things that we've defined. All of these things are defined in terms of the dimension, which is the height of the duct, h. And so the calculation sequence, now that we have those, so the velocity is 100 divided by 3h squared, the hydraulic radius is 1.5h, pressure is equal to a friction factor we don't know, and a term that includes h on the right-hand side as well. And then Reynolds number is also defined in terms of a function of h. And so what we can do is just use this in a sequence. So the sequence is that we use friction factor to calculate a size for the given flow. We use this friction factor to calculate Reynolds number, and then we use that Reynolds number to check the friction factor. So what we do is we choose a friction factor, we use that to calculate a Reynolds number, and then we recircle the wagons to make sure that the Reynolds number satisfies the friction factor, and if it doesn't, we modify it. So I said before that one thing you notice about friction factors is they don't change very much. It's a log scale, and so between this point and this point, it varies by an order of magnitude. It varies between 0.1 and 0.01. So you should pick a number somewhere within there, probably. And so in this particular example, a selected number is 0.02. And then so you can use that friction factor to calculate the head loss in the system from equation 3, which is friction factor. So what's H5? This term, well, where is it? This term here. This term would be H3 on this term. So in other words, you can use this to calculate. So if you know a friction factor, you can put a magnitude in for the friction factor here. You could use that to calculate a value for H. With that value of H, you can use that to calculate a Reynolds number. So actually what I'm going to do to make this clear. So this is the first one. So you choose a friction factor. You use that to calculate a value of H. You use that value of H to calculate a Reynolds number, and then you use that Reynolds number to calculate a value of friction factor to check whether it stands or not. So here, if you use a friction factor of this, you can use that to calculate from this expression here that the value of H is equal to this term. You can take the fifth root of it and you get a height of equal to 1.03 meters. And you can use that as your characteristic dimension in the Reynolds number, which has a friction factor on the bottom. And you come out with a magnitude of Reynolds number, which is 3.2 times 10 to the 6. You go to 3.2 times 10 to the 6. So this would be 4. This would be So what is this? This is 10 to the 6. This is 2 times 10 to the 6. This is 3 times 10 to the 6. What was it? 3.32. 3.3, I'm guessing might be, why is 3.4? Yeah, I don't know if I've been using this in this or not. 3.36 on a smooth pipe would give you, is that right? Is that through 1, 2, 3? What are these? 1, 2, 3. I can't see what the divisions are. I think it's this one, but anyway. If it's a smooth pipe, it would come across to being roughly 0.01. You'd use a friction factor of 0.01. 9.6 is pretty close to it. You use this value in this equation to be able to solve for H. The value of H you get from that equation is equal to 0.89 of a meter. You use the value of 0.89 of a meter in this expression here to get the Reynolds number. The Reynolds number comes out to be 3.84 times 10 to the 6. And I guess that's what this is here. You use this up here and go across, and you end up with 0.0093, which is this number here. You use that in this expression again to be able to calculate the value of H from the pressure drop. The value comes out to be 0.884. You use that in Reynolds number to calculate what the Reynolds number, and the Reynolds number comes out to be 3.87. The one you calculated before was 3.84. And so the difference between these is so trivial that the value, if you go back to this chart, you'll end up pulling off the same friction factor, and you end up with calculating a value for the head loss, which is equal to, the height of the tube, which is equal to 0.88, almost 0.9 meters. And therefore, if you know that, you can calculate that if this is 0.9 meters in height, then the width of it is 3 times 0.9, which is 2.7 meters or so, right? So that's it. So the point is, I guess, that it gets kind of complicated when you come to solving for the geometry, because as the geometry changes, your velocity changes because the cross-sectional area of your system changes, and the friction factor changes, which changes your head loss. So this is a function, this is proportional to the friction factor. So both the velocity and the friction factor change in the same time, so you have to iterate to a solution that you get a solution that matches all your requirements. So that's pretty much it. I think that was the only example I was going to do. Yeah. So I'm not sure I did a great job, but you get the idea. The point is that all of the parameters you have to use, and in this case it's for a non-circular section conduit, so you have to calculate the equivalent hydraulic diameter to start with from this particular duct, and then you need to be able to define velocities, Bernoulli's equation for the friction losses, and the Reynolds number, all in terms of some item of the geometry. And if you have that, you can go through it just to work out your way to a solution. So a pain to be able to do if you have to do it, but to dimension pipes, that's the only way you have to do it. All right, we're at the end. Any questions on that magnificent performance? No. All right. Next time we'll talk about pipe networks. So the stuff for the next midterm stops here. Pipe networks don't exist on that, and so on the final component, the final, which is such it is usually pipe flow networks, external flows, and open channel flows. And they're even more formulaic than the third midterms are. And so, as I say, progressively, the questions get a bit more predictable and recipe-like in terms of solving them. So, yeah.
Are we in person the week after Thanksgiving for classes?
No, we're not.
We're not?
You never see me again after Friday.
Oh, wow.
I know you'll be.
Oh,
I know you'll be gutted about that. No, we're not. We were going to have week 8 because I was going to be in 8 countries in 5 days on Zoom, but I completely forgot about it. So we ended up in the classroom, you remember? So I just shifted that. We were always, I think, going to be out on week 13, which is the week after Thanksgiving. I just switched it so that next week we're not here. So thanks for reminding me. I don't need to announce it today, but I could use that reminder on Friday.
Okay, thank you.
Yeah, so no costs after that. So then it'll be extra credit stuff for next week, midterms the following week, and then Thanksgiving, and then back after that, and it's online on the week after Thanksgiving, and then it's a Friday, Monday, Tuesday exam, as I mentioned last time, so that nothing in the final week of classes is worth more than 10%, which is a useful university rule, I think, that protects the students from being overworked. So the professors don't put a final worth 50% of your grade, and you have 5 courses with 5 finals worth 50% of the grade in each class in your final week, the week before finals. So that's it. There is an assignment due, right, on Thursday, and we'll get together for those who wish to join us on Friday, and we'll talk about pipe networks. And pipe networks is just where you have either pipes in parallel or pipes in series, and also pipes in branching systems. So we'll talk about that. Okay?